All right, good evening. Working on some compound interest and exponential growth and decay formulas here. So first problem, number 57. You got to use this formula. The amount of money is equal to the principal, the starting money, times 1 plus the rate divided by the number of times it gets compounded per year raised to the number of times it gets compounded per year times t, the number of years. Okay. So just in this problem, you have a rate of 2%, which you got to turn to 0.02. Your P is 2,500 every time. And then your N is going to keep changing, and you're going for time of 10 years. And so here's what we got to do. We got to do 2,500 times 1 plus 0.02 divided by 1 raised to the 1 times 10 power. So, I mean, you can type this into your calculator. Here's what it's going to look like. 2,500 times parentheses 1 plus 0.02 divided by 1, close parentheses, raised to the parentheses 1 times 10. Now, if you type this one in, you can just use the second and then the enter button. It'll bring it back up, and you have to keep changing this number. The other numbers don't have to change, okay? But that number, the 1, because you have to do it for 1, 2, 4, 12, 365, and continuous. When you do it for 1, you're calculating. I don't know what Mr. Prussing's going to want, if he's going to run these rounded to the nearest dollar, but this is going to be $3,047.49. And then you have to change that to 2, so you do 2,500 times parentheses 1 plus 0.02 divided by 2. So this means you're compounding your interest twice a year. Divided by, raised to the 2 times 10 power. So type that one in and use 2 there. All right, you get 3,050. So you get a little bit more money. That's because you're compounding a little bit more often. So if you compound more often, you get more money. And then you got to change those numbers to 4, 2,500 times 1 plus 0.02 divided by 4 raised to the 4 times 10 power. So that's going to get raised to the 40th power, but you're dividing the interest rate by 4. So it kind of balances out. You're going to get a little bit more money. This one's really close. You're only going to get to 3,050.99. I think I did those right. You can always check my math. But, all right. So then you got to keep doing these. Keep doing them. So then you got to do 2,500 times 1 plus 0.02. Now divide by 12. So you're going to compound it 12 times a year, raised to the 12 times 20 power. All right. So this is going to be 3,053 dollars. And then you do for 365, 2,500 times 1 plus 0.02 divided by 365. So the 12 is compounded monthly. This would be called compounded daily, okay? This one would be monthly. The one with the 4 would be compounded quarterly. This would be daily compounding. Daily compounding is going to give you a little bit more money. You raise it to the 365 times, oops, that's not times 20. I don't know why I changed that to it. That should still be a 10 up there, times 10. So this one is going to be $3,053.49. I think these are all right. And then the last one is compounded continuously, and that's going to be this formula. I call it the PERT formula. But you're going to take 2,500 times E. And, this one doesn't need parentheses. You get the E up, and then it'll have the raised 2, and then you're going to type in 0.02, that's your rate, times 10 years. So in this one, the rate and the years go up in the power position. The rate and the years are up there in the power position, right up there. And this will give you even more money, but not really that much more, only 2 cents more. According to my calculations, $3,053.51. So that's what's supposed to fill in the table for 57. I don't think I made a mistake on any of the calculations, but I'm questioning myself. So you can try check in the back of the book too. This is not a numbered problem. I didn't check it in the back of the book. Okay, so there's that one. But notice what kept changing. Kept changing here and there, here and there. Otherwise, everything else stayed the same. You can use the insert key and the delete keys. And then we change it to 12 and 12, and then we change it to 365 and 365, and then we did this one, which is compounded continuously. All right, next one. Next one was some all compounded continuously for different amounts of time. So they kept changing the t. They wanted you to do for t equals 1, 10, 20, 30, 40, and 50. So those are different amounts of years. This one, they gave you $12,000 to start with, and a 4% interest rate, which is 0.04. Okay, so for 1 year, compounded continuously, you'd use the PERT formula, 12,000 times E raised to the 0.04 times 1. All right, gotta make sure you put parentheses around that. All right, and then you're going to do it for 10 years. So it's 12,000 times E raised to the 0.04 times 10. And then it's 12,000 E raised to the 0.04 times 20 years. So you can kind of see it just keeps changing here. You could put a times in between the 12,000 and the E, but your calculator will know that you're multiplying the 12,000 times the E raised to piece. I'm going to just write them all out here. 12,000 E raised to the 0.04 times 30 years. 12,000 E raised to the 0.04 times 40 years. Now you should close the parenthesis, but it turns out your calculator is okay if you don't, but I was good to have it to close the parentheses. 12,000 E raised to the 0.04 times 50. So after 1 year of compounding continuously, you'll have $12,490. I'm going to round these to the nearest dollar. There's a lot more decimals, but I'm going to round to the nearest dollar. 10 years, you're going to have $17,092. 20 years, you're going to have 26,706. 26,706. 30 years, 39,841. 40 years, 59,436. And 50 years, you're going to have $88,000. $88,669. That's a lot of money if you can leave it alone for 50 years. All right, that's cool. So you kept changing. We kept changing the amount of years. So that's why this is the number we kept changing every time. All right, and our money kept growing because we're leaving that money in the account for more years. All right, next question is kind of the same thing, $12,000. But in the next question, you're going to change this interest rate here to 0.035. So it's kind of boring because it's all the same stuff. 12,000 E to raise to the 0.035 times 1. So E raised to the 0.035 times 1. I should put times 1 in there. And then it's E raised to the 0.035 times 10 years. And 0.035 times 20 years. So it gets pretty redundant. So you start with $12,000 every time. And then you just keep changing this year times 30, times 40, times 50. But it's always at 12,000. And then E, 0.035. All right, so I'm not going to write those all out. I hope you guys are okay with that. But after 1 year, this $12,000 is only worth $12,427. Now, these numbers are all going to be smaller than problem 61 because the interest rate is lower. After 10 years, you're 17,029. That's a little bit less than 10 years on the previous problem. In 20 years, 24,165. Then you're going to have $34,292. So Now that's a lot smaller. In the 30-year one for the 4% interest rate, you had $39,849. So you're like over a $5,000 difference. 40 years is 48,662. And then 50 years, 69,055. All right, so still get to a lot of money after 50 years, but that's almost $20,000 less. So if you can raise up that interest rate, this one it's a little bit lower. If you get a better interest rate, you'll make more money. All right, last two questions are some application questions with some exponential decay and exponential growth. So, what do we got here? So first one was the half-life. I don't have the book with me, but the half-life of a compound is 5,715 years. So if you start with 10 grams, and then half-life would be 1/2, and then you raise that to the t divided by 5,715. So that's the formula. Okay. Now if t equals 0, you would have 10 times 1/2 raised to the 0 divided by 5,715. The order of operations, we kind of have to do the math within the exponent first. Well, that's going to be 10 times, and you can use a decimal here. I type this in. I mean, you don't have to type this one in your calculator, but it's going to be 0.5 raised to the 0 power, because that's what 0 divided by 5,715 is. That just means you had 10 grams, because this part's going to turn into 1. 10 times 1. So 10 grams to start with. All right, part B says, how much do you have left after 2,000 years? So here you're going to have to type in 10 times 0.5 raised to the 2,000 divided by 5,715. So it's going to do the parentheses first, then it's going to do the 0.5 raised to that decimal, and then it's going to multiply by 10. After 2,000 years, you're still going to have 7.85 grams of this substance left. And the reason being is because 2,000 years isn't even the half-life. You have to get to 5,715 just to get down to 5 grams, just to cut the amount in half. So 10 grams for t equals 0, 7.85 grams for t equals 2,000. And then for part C, it said graph it till 10,000 years. So your graph's going to kind of have a look like this. Okay, I'm going to just go from 1 to 10 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we know at time 0, we have 10 grams of that stuff. And we just did the year 2000, so let's just go 1. So here's 0, 1,000, 2,000. So at year 2000, you're still almost at 8 grams. Count up 1, 2, 3, 4, 5, 6, 7, 8. Just underneath 8. Be right about there. And now I did it one more time. I did it 10,000 years, because they want you to do 10,000 years out. So I did 10,000 divided by 5,715. And I did 10 times 0.5 raised to that. And even after 10,000 years, there's 2.97 grams left. So at 10,000, you're still just underneath 3. So it is going down on a curve, but it's a pretty shallow curve. All right, that's your exponential decay. Okay, exponential decay for that. All right, last question. Last question's about growth in the state of California's population. So they're saying in 2015 they had 34.706 million people, and the rate of growth is 0.97%. So they have this formula, E.0097 times T. So all that stuff is up in the power position. So population equals, so 2015, actually, sorry, that isn't right. 34.706 is not 2015. I don't know what that year is, but I'm not worried about it. They want you to make a graph of 2015 to 2013. So they're saying 2015 we're going to use 15. So 2030 we're going to use 30 when we plug it in. So to see the population in 2015, we're going to have to take 34.706 times E raised to the 0.0097 times 15. And you're supposed to use, I use Desmos. You can use your calculator to do this too. But the population in 2015 is 40.14 million. And then I used Desmos to tell me what the population was in 2030. So I put 30 in right here instead of 15. The population was 46.43, so it's growing. All right, and I did actually 2020 and 2025. You could go in 1 year increments too, but it's a lot of typing. 42.14 and 44.23. Now, they did say for Part A to look at the graph just from 2015 to 2030. And the graph is actually just looking like a straight line if you're just looking from there to there. It's hard to even see any curve at all. But in 2015, it's at 40.14 million. So this is like 40, and this is like 50. Whoops, sorry, 50 would be like right up there. So even at 2030, it's not up to 50 million, okay? So that's kind of Part A. This is Part B. And then Part C, it said, when will it actually jump to 50 million? So I just kept, in my table, I typed in, I looked at what 2031 would be, 2032, and finally when it gets to 2037, in the year 2037, it's like 49 point something. And then at 2038, it jumps above 50 million. So that's it. That's all I got for you.